So I want to try and do what we were doing with circuits and cycles for regular graphs in diagrams. I would also remind you that, unless I'm grossly mistaken, I'm moving into a new chapter, and that means I've completed 3 more chapters. The homework for this last section in chapter 6 is due on Friday. We should have an exam after that. Guess what's Monday? In case you hadn't been keeping an eye on the calendar like I hadn't. Okay, so let's consider 2 graphs which model a pair of cities as shown on page 161. Here we go. Streets, blocks, I turn intersections into nodes. I have 2 different graphs. The one on the right has a bridge, the one on the left doesn't. What do I know about trying to do a circuit or a cycle on the right? Why not, Abigail? As soon as I have a bridge, I have a cut vertex. As soon as I have a cut vertex, it's not Hamiltonian, it's not Eulerian. It could have a path, but not necessarily a trail, not necessarily a circuit or a cycle. I could be a real pain in the neck here. What if in the graph on the left in town A, all of those roads were suddenly one way? Well, that turns this into a digraph. I don't know at first glance if that graph is Eulerian or Hamiltonian. It's not that difficult to figure out if it's Eulerian. How do you know whether it is or isn't? Okay, and I see right here a vertex that's of degree 3. It's not Eulerian. But it could still be Hamiltonian. I don't know. Not sure off the top of my head. But if I make it one way, is it still? All right, wait a minute. Let me go back to my definition. Almost always we label a digraph as D rather than G. So I have vertices, and instead of edges, we call them arcs. Or directed edges. That means they have a from and a to, and they're ordered. So I'll use ordered pairs instead of set notation. Quite frequently, digraphs have some places that we do think of as going back and forth. But I would mark those as separate arcs. I'm not using an edge in both directions. I make them arcs and add them both. So if for every u and v in the vertices, let's suppose we have at most one of the arcs from u to v or v to u. Can't have them both. We could have none of them, so those 2 vertices wouldn't be adjacent, but we have at most one. Then that's an orientation of my digraph. We call it an oriented digraph. Now I can take a regular a regular graph, and put an orientation on it. There's just one problem. Given any graph, how many orientations are possible? That only counts for one vertex each, right? Yeah. But if I look at a graph on page 161, that's completely simple graph, not oriented. How many different ways can I make those streets one way? A very big number. Regular ordinary counting principle. That would only mean somehow the number of changes went down. Oh. It'd be 2 to the number of edges. Some orientations are nicer than others. If a graph contains any pair of vertices where there are both edges available, I've lost my orientation. That's now just a regular digraph, not an oriented digraph. To that end, I was going to write an arrow, but then I realized it would cross lines. That's not a good thing. A symmetric digraph, if ever I have a UV edge, then I have the VU edge. But that is the same as saying that every road is two-way, isn't it? That's just a regular graph. So symmetric digraphs are a rare occurrence. They are needed to model situations where information or objects can only flow in one direction, but that there are still paths back, even if they are separate paths. That's the important thing. It keeps stuff separated in each direction. So each road is one way, but for every one-way road, there's another reverse road. That's really complicated. I don't know why you would do that, but that's why I'm not in road design. There was some other terminology we used about adjacency. Because we were looking at edges that go in one direction, I changed my words for adjacency. So let's suppose I have an arc from U to V. Well, then I'm going to use those words in describing adjacency. I can go from U to V. So U is adjacent to V. V is not adjacent to U. Because that edge only tells me I can go from U to V. That means that U is adjacent to V. V is gotten from U. So if my arcs are one-way roads, I change the way I think about degree. Because degree now, direction matters. Before I was just saying, well, how many edges, how many other vertices are we adjacent to? I could be adjacent to, or I could be adjacent from, right? That makes a difference. I need to count my degree differently. So the out degree tells me the number of arcs that come out, or in other words, the number of things U is adjacent to. We're going from U. And therefore, we'll call the other way the in degree. ID is the number of arcs that end at. So the number of things V is adjacent from. Once someone finishes writing down this theorem, I want y'all to tell me what the hell it means. And then tell me why the proof of this is absolutely trivial.
Since there are arcs, they only get in or out. It's not like adjacent curves. So however many you have going out, you have the same going in.
Every arc has to go from somewhere and get counted once here to somewhere and get counted once here. I think that's the shortest proof in this entire class. This is the directed version of the handshake theorem. We counted each edge twice. Nope. Nope. Now we only count them out once and in once. For every digraph, I can have a sub-digraph, just like for every graph, I can have subgraphs within it. So we can talk about sub-digraphs in the same method that we talk about subgraphs. And we'll be looking for particular kinds of subgraphs. Most of these terms I think we did before, but it was back in chapter 1, so it's been a long time. Questions? This should look familiar. A sequence of vertices in my digraph. Wait a minute. A sequence of vertices in a graph is called a walk. So this is a directed walk, provided what? Yes, but more than that. Not just connected. Which means I need to know all the one-way roads point in the correct direction. So the question is, can I get there from here? Are all the one-way roads pointed in the correct direction for me to get there? The next 5 minutes are the same definitions from undirected graphs. The number of vertices, the number of arcs in a walk is called, size has a specific meaning for a graph. For a walk, we use length. So that one up there has length K. No repetition of arcs. If it doesn't repeat vertices, a path. Every path is a trail. That was definitely true in undirected graphs. Because if you went from A to B, then to go back, you'd have to go across the same edge. But I don't know that that's true here, because there could be an edge in each direction, an arc in each direction. Oh, I got to be careful. A walk from U to V is closed if starts and ends in the same place, and open otherwise. Again, I'm redefining the same terms in my new setting. And so almost all of my definitions are going to parallel each other. Closed trail, the length at least 2. Oh, I caught you. Which one is it, a cycle or a circuit? Because in a trail, I'm allowed to repeat a vertex. In a path, I'm not. I always try and remember circuits go with Euler. And Euler wanted to visit each edge once. But I could visit each vertex as many times as needed. Hamilton wanted to visit each vertex once. Hamilton goes with cycles. So if I remember the stuff we just finished doing, I can help remember which one is which, I think. Notice the emphasis here on internal vertex. If I have a closed path, I am definitely repeating a vertex. So I really can't call it a closed path. Paths don't repeat vertices, damn it. It's a closed walk. It might be a closed trail. Notice this is not an orientation of G. Why is D not an orientation of G? And an orientation is only allowed to contain at most one arc from any pair of vertices, either to or from. In other words, I would take G and I would put arrows on top of each thing, but on this edge I put 2 arrows. That's not allowed. An orientation can only be 1 arrow on each at most. Okay. Circuits, cycles, walks, etc. Can I get from Y to U? Sure. Y to W, W to V, V to T, T to U. Over here, without direction, I could go in one fewer step, couldn't I? Adding direction to my edges changes distances. The roads are one way. The most common sentence I heard when I first moved to Pittsburgh was, "Oh, you can't get there from here." In that same vein, on the right graph, if I want to go from Y to Z, the distance is 1. Go to the left graph. Can I go from Y to Z? Yeah, but the distance is a lot longer than 1, isn't it? Or 1, 2, 3, 4, 5, 6. That one's shorter. Say again? Oh, I can, because I said Y to Z. That is up. I can go 1. I looked at the wrong arrow. My apologies. Good catch. Yeah, if I want to go from Z to X, I'm in trouble. I have a big problem if I want to go from Z anywhere, don't I? Oops. There are places where taking the graph directions away is beneficial. So if I remove the directions from a digraph, I get an underlying regular graph. Now, technically, if I just remove the directions from my edges, I would still have multiple edges in that digraph because I had 2. One went from T to W and one went from W to T. But if I remove the duplicated edge as well, replace it with a single edge, then I get a simple graph. Our textbook always uses the underlying simple graph rather than an underlying multigraph. So they say the underlying graph, they mean remove the multiple edges as well. Questions? Ben, you defined it, you used the term earlier, connected, right? What was the definition of connected? Hmm? Yeah, what's a connected graph? Adjacent would mean they're connected directly.
Connected meaning that's, yeah, from any vertex to you.
You just said the magic words. From U to V. What did we just say about Z on that graph we were looking at? I couldn't leave Z. In that picture, if I'm at Z, I can't go anywhere. There are no roads out of Z. It's the Roach Motel. You can check in, but you can't check out. Oh, sorry, that commercial is older than most of you. On the other hand, lots of other vertices here, I think every other vertex has both arcs that go in and arcs that go out. Z is the exception here. Huh. So connected is more complicated because when we were talking about connectedness, we talked about a path from U to V for any pair of vertices. Technically, that makes this graph not connected. That's stupid because this underlying graph is connected. So this should be connected, but it's kind of weird. Well, if I do that, then I might as well just say, hey, look at the undirected version. And then I'd be able to find a path from anything to anything else because I no longer care about the orientation of the roads. But I've taken away the direction from it, right? I'm going to call that weak connectedness or weak connectivity. So I'd say my graph is weakly connected. Then I only have to be able to get in or out. A strong digraph, a strong digraph, or a strongly connected digraph is one where I can get from U to V and from V to U. So not only can I get there, I can get back. And that's why the example we were just looking at is a weakly connected graph, because once I got to Z, I was screwed. messes with my idea of distance. Messes with my idea of distance. I'm going to have to change my definition of distance then, right? So let's go back and remember how we defined the distance between two vertices. The distance from U to V. The distance between U and V. What was our definition? The length of the shortest path. And in an undirected graph, this was an equivalence relation. If I fixed a vertex and I said measure from here, then you'd say, oh, all of these are distance 1, all of these are distance 2, and it was summative, and it was symmetric because if I could get there, I could get back. In a digraph, that fails right there. May not necessarily have a path back. I can only guarantee you that the directed distance works for every pair of vertices if the graph is strong. So I'm going to change the symbol. It's like a vector. The oriented distance from U to V. There's the caveat. It's the length of the shortest path from U to V, if such a path exists. If no such path exists, this distance is undefined. Some textbooks will tell you, therefore, the distance is infinite, which is also a convention used in the original distance definition. If you have a disconnected graph, vertices that are in different components are at a distance of infinity from one another. Remember when we did Prim's algorithm? With the matrix, we wrote all those infinities in there, and I changed them and just put dashes in there. You can do it either way. You can say that distance is infinite, or you can say that distance is undefined. What can you tell me about degrees? if you know your digraph is strong. I'm in a digraph. There are two different kinds of degrees. So which kind are you talking about? They're both present, but are they necessarily both even? I am in a digraph. I have to talk about in degree and out degree separate from one another. And in that case, the total degree at one vertex does not have to be even. Because I could have in from one and then out to two, right? The total degree could be 3. Now, if you're thinking even, well, then you're thinking the other ends as well. I'm only thinking at one vertex. Reese?
Like the number of vertices in the graph.
Would what be equal to n?
That would be in degree over out degree.
I don't think so. Let's go back and look at that picture we were just looking at and see if we can check. This is not strong, but it could be if I turned one of them around, right? Either this one or this one. I'd be able to deal with that. But then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 edges. The out degree and in degree totals are 11, but there are only 3, 4, 7 vertices. Aha. That was the problem right there about being strong. I couldn't get out of Z. So if D is strong, then in degree of V is positive and out degree of V is positive. For all V. Now that is a one-way sentence. That's an if-then. This is a necessary but not sufficient condition. Knowing that everything has positive in degree and positive out degree doesn't guarantee me strong. I might be able to get from U to V, but not be able to get back from V to U. Even though I get in and out of everything, I might be stuck somewhere. Page 164. Let's go from X to U. Well, that's easy. X to U. Now go back. The only way to leave U is UV. Once I get to V, I can only go to Z. Once I get to Z, I can only go to U. I'm trapped in that little triangle over there on the left. So in spite of the fact that I get from X to U, I can't get back from U to X. That's not strong, but every vertex has positive in degree and positive out degree. So that's this condition is only if it's strong, then I'm guaranteed this, not the other way around. But if I can get there from where a U to V, there's got to be a shortest way to get there. There might only be one way to get there, but there's got to be a shortest way to get there. This sounds awfully familiar. The only thing that is different in this theorem than the same version that we proved previously is that I'm using a directed graph instead of an undirected graph. So how did we prove this last time? I got to go back and look that up. Wait a minute. We said here's a walk from U to V. Now let's take a path from U to V. Path means shortest possible. It means what? No repeated. So if my walk is already a path, that's the same length. I didn't repeat anything. If I did repeat something, then at some point I had to come back. I had to come back in a one-way fashion. I can still keep going, right? So let's just cut that little loop out. I've made a path that's shorter. If I take the minimum possible length path and then say, oh, you can make one shorter by cutting out a loop, then you didn't have its smallest path in the first place. The shortest path from U to V is called, sorry, what? A geodesic. Again, because of the lack of symmetry in my distance, a UV geodesic may not be the same length as a VU geodesic. You might be able to get from U to V directly, but V back to U might take much longer. If they were both the same exact length, that's okay. But they have to go through different things, probably, if they're all one way. If they all go through the same things, then my graph is symmetric, right? And if it's symmetric, then it's not directed, which is not helpful. More on Friday. Hope you all have a wonderful rest of your day. I will see you then.